Hello everyone, it's Keyvan Mirehbar. I'm a predoctoral researcher from IMDEA Energy, and today I'm going to talk about the use of electricity for removal of pollutants from wastewater. In this lecture, we are going to talk about simultaneous water treatment and CO2 valorization, basics of hybrid photoelectrochemical reactor, and electrochemical oxidation of water. And the objectives here are how electrochemical cell works, fundamentals of electrooxidation of pollutants in water, and features of electrodes in wastewater treatment. So, past few years, human activities has risen a lot, and it's causing two main problems that we have on Earth, which is climate change and water contamination. With the conventional wastewater treatment plants that we have, maybe we need to do some modifications and do some evolution to some new systems and improve the current situation to better wastewater treatment plants by having a system that can simultaneously remove CO2 from air and do water treatment by only use of sunlight. So the HySolChem project is offering an idea in this project from different countries across Europe. We are gathering together to design a photoelectrochemical reactor to do CO2 reduction simultaneously at the same time with wastewater treatment. So how it works, we are going to build a hybrid photoelectrochemical reactor at the TRL5 scale that basically it's a photoelectrochemical cell that on the cathodic side we have a photocathode that we reduce CO2 to products such as ethanol, ethane, methane, and other products, other type of products. And on the anodic side, we remove organic pollutants by oxidation to CO2 and water. So let's see what's going on the anode of this photoelectrochemical reactor. So on the anode, we usually have electrochemical oxidation. So what is electrochemical oxidation? Is when we are losing electrode on the surface of the electrode. So when you have an electrolytic cell, you use electrical energy to drive non-spontaneous redox reaction. So imagine you have a system filled with water and you put the electrode inside and you apply electricity and you force certain reactions, certain materials to lose electrons on the anode, which cause oxidation on that state. So this reaction can be used in different applications, such as methane oxidation to methanol, urea oxidation, alcohol oxidation in biomass conversion, water splitting, or wastewater treatment. So here in this lecture, I'm going to focus on the water splitting and wastewater treatment. So when you apply electricity to water, you are breaking water molecules. So for doing that, the reaction goes through 4 steps. At the final step of this reaction, you break the water molecules and you have hydrogen and oxygen. But this is not everything that you can produce. You can also produce hydroxyl radicals while you are breaking water molecules. So why these hydroxyl radicals are important? So these hydroxyl radicals can survive us from having those pollutants in wastewater. So basically these hydroxyl radicals are highly reactive, they are non-selective, easily generated, powerful oxidants, they have a short life, they are harmless, and they can control the rate of the reaction. So by having these hydroxyl radicals, we can attack the organic pollutants that we have in any type of water to oxidize them and produce simpler molecules. So how it works? So when you have hydroxyl radicals, as I said, they are highly oxidants. So they attack the organic pollutants, and at the end you produce CO2 and water, and you decompose all those organic pollutants. So it's really good, but what are the drawbacks of commercial electrodes of this certain reaction, electrooxidation of water pollutants from water? So right now, the technology that we are using electrodes such as PbO2, boron-doped diamond, and dimensionally stable anodes, usually from iridium and ruthenium, which are expensive, in some cases toxic, and they have short service life. But HySolChem here is to survive and give a new insight to the electrode technology for this reaction. So in this reaction, instead of all those traditional electrodes, we are going to use multi-metal oxides as electrocatalysts that can be cheap, non-toxic, and abundant. Why we are using multi-metal oxides? Because basically these materials, they can be tuned as we want, and we can design some kind of materials that can be used for our benefit, which in this case is to produce more hydroxyl radicals. In this case, we came up with the idea to use nickel and manganese and produce compounds such as nickel manganese oxide and use them as an active material for our reaction. On the other hand, all the electrodes, they must have a substrate. In this case, we are going to use a 3D porous conductive substrate because they can increase the contact surface, they can increase the reaction rate, high specific surface to host electrocatalyst, they facilitate a flow-through design. There are plenty of options to use in this case, such as reticulated vitreous carbon, graphite felt, aluminum foam, and nickel foam. And in this case, as a preliminary stage, we started to choose nickel foam as the substrate for our electrode. So how we prepare these electrodes? We synthesize these materials, nickel manganese oxide. It's called hydrothermal reaction. So we add the precursors, we mix them, we add them to some containers, and we heat them for 12 hours, 150 degrees. And after that, we need to do the calcination, 5 hours, 450 degrees, and we get these materials such as nickel manganese oxide. In order to produce electrodes, we need higher amount of materials, so we need to scale up this process to produce more materials, and from those materials, we prepared the electrode. As I told you, we used nickel foam as a substrate, so by deep coating, we just submerge this nickel foam to the ink that we prepare from these materials, and we prepare our electrode from this, which is nickel foam alone, with this nickel foam covered with this material, nickel manganese oxide. In order to do the reaction, as I told you, we need electrochemical cell. As I told you, every electrochemical cell, it contains a cathode and an anode. In this case, since we want to do electrooxidation, we need to put our electrode as an anode, and on the cathodic side, we just circulate water. We produce hydrogen on the other side, but it's not the main concern at this point. We just want to see how we remove pollutants from wastewater. In this case, we used phenol as the pollutant to study. I want to show that. Let's get the pointer. Yeah. And we designed this cell and we 3D printed. As you can see, we have the cathode, we have the anode here, and we have the membrane to separate the anolyte and the catholyte, since later on with the whole system we want to run both reaction at the same time, CO2 reduction and wastewater treatment at the same time. So according to the results, we compared different electrodes. The red one, nickel foam, nickel manganese oxide, is the electrode that we we thought it's going to work better. And as you can see here, in case of removal efficiency of phenol from wastewater, in only 2 hours, we could completely remove all the phenol from the wastewater samples. We also checked COD. COD is abbreviation of chemical oxygen demand. Chemical oxygen demand basically indicates how much organic pollutants you have in your wastewater sample. It's not just phenol, all the intermediates that you also produce from those phenols that you have oxidized are also in this are included in this COD measurement. So as you can see, we could remove 80% of COD also in 300 minutes. And at the end, we compared this electrode with the state of the art, with the commercial electrodes that earlier I told you about, bronze doped diamond and dimensionally stable anodes from ruthenium and iridium. And as you can see, our electrode is performing much more better than all those commercial electrodes. So what we have learned so far in this lecture, what electrolytic cell is and how it works, how electricity can remove pollutants from water using hydroxyl radicals and as an oxidant agent, how newly developed electrodes are prepared, and the achievements of the projects. A hybrid system is being developed. We are developing this hybrid system for CO2 reduction and wastewater treatment. The electrode that we have prepared as an anode was able to remove 100% of phenol from samples and 80% of COD from water. And this electrode was compared also with the state-of-the-art bronze doped diamond and dimensionally stable anodes, and we could see it can perform much more better than all those commercial electrodes. I would like to thank my colleagues from HySolChem project, European Union, Horizon 2020 for funding this project. And also I would like to thank people in my unit at IMDEA Energy, Electrochemical Processes Unit. And thank you so much for your attention. I hope you enjoyed this lecture.